1 second to come to the top. Then it will drop from the velocity goes to 0 and finally to the bottom. And the overall distance of this acceleration is 10 meters. So I give a half gt square equals to 10 meters. Finally, we got time equals to the square root of 2. Therefore, after the time of 2 and the acceleration of g, the final velocity is the square root of 2 times g. That is the final velocity for the situation 1. And then for situation 2, is with the opposite direction of the velocity, that is point to the downside. Therefore, with both initial velocity and acceleration, the new equation is v0 t plus half gt squared, and finally equals to the overall distance by meter. And the final result is v0 is 0, L is known, g is known. The only unknown thing is the time. And then finally, I got the time. The value of it is the square root of 2 minus 1. Therefore, with a started velocity of 10 meters per square and the acceleration of 10 meters per second square times the time, the addition of these two values will finally result is half 10 meters per second square, which is exactly the same equals to the situation 1. So why does this situation got a same final velocity? Actually, we don't need to do this calculation because we have a much more easier way, and that is to use the potential energy. Because no matter situation 1 and situation 2, although the path and the time it takes to come from the starting point to the ending point is different. Both the time and the path is different. However, there is one similar thing, that is the starting point and the ending point, and the change in the potential energy that is given by the gravity. And the potential energy is the starting point and the ending point. At the very beginning, kinetic. At the beginning, the kinetic energy of these two situations is the same, and they both equals to half m squared. Kinetic energy. The m is the same, and the velocity is the same because the velocity square will ignore the direction of it, and they are both with a value of 10. And finally, at the ending position, its energy is changed, and it is changed with another potential energy that is work done by the gravity, and the work done by it is Fs, right? So in this situation, F is mg, S is 5 meter. both these two terms, the energy is changed from health and velocity square with the addition of another work done by the gravity, and that is mg phi. So L mv square is the addition of y and g is a final velocity. Do the calculation again. For the n can be raised L v square, and the started is 10 plus y L v square 10. Right? You'll find it exactly the same as we calculated with the velocity and acceleration, and it was much easier. So then we are going to know what is the potential energy. Potential energy is another energy that is not belongs to the point what we learned. However, it can be transferred into the point what we studied by the work. The similar, when we climb upstairs all the way to this room from one floor and to the second floor here, the potential energy of us also has changed. If the height of the second floor is 5 meters, the potential energy that is increased from 0 to m, the mass of us, and the g, and 5 meters. That is what we, the potential energy of us, increase when we climb the upstairs from the one floor to the second floor. There's a more potential energy. Gravity always related to potential energy. And then there's much another thing. For example, this is plastic. Since that is with elasticity, like spring, there is a potential energy in it. That is the most common things that is related to electric, that is related to potential energy. First one, gravity. Second one, things with elasticity, like the spring. And the third one, electric field. That is what we are going to learn in this class, the electric potential. What we want to learn, the goal is how to calculate the electric potential energy of a collection charge and the meaning and the significance of electric potential. Then, how to calculate the electric potential that a collection of charge produces at a point in space. Then, how to use electric potential to calculate the electric field. The tools the two red one is the most important. That is the define of the work. I have already thought about that. Then,
But Laoshi,
I
there is the four cases. There is first is gravity, and there is always on the earth there is gravity which is pulling everything on down, and elasticity when we apply some force on elasticity.
yes.
When we remove the force, then elasticity comes back. And the same to spring, but how can electric field go in the same case with that thing? Because they all have the returning force.
You mean you think the potential energy in the electric field is different from the potential energy in gravity and in the spring?
Yes.
Good question. Situation one. There is gravity and now the other force, only gravity. And there is a point. There's another point. The direction of the gravity is pointed from up to the downside. And there is situation two. There is an electric field. Electric field, okay? And no gravity. No gravity. Situation two. There's a charge with a mass of m and a current of q. For gravity, at the position A, then it moves all the way to the position B. One, how much is the work done by the gravity from A to B? And the second one, how much is the variation in the potential energy of gravity? The work done by the gravity may be force times displacement, and that is mgs, right? Potential, the variation in potential energy, mgs, right? That is the transformation of potential energy of gravity into the kinetic energy of the M. Maybe the velocity is increased or the other energy of the point is increased, right? That is a transformation of potential energy into another kind of energy of the point. Then, for the electric field, how much is the force on the Q? Force because of EQ, right? EQ. Then, question number one. How much is the work done by the electric field from point A to point B? And then, question number two. How much is the variation in potential energy of the electric field when the point comes from point A to point B? What's the one? The work done by Fs, right? And that is EQS. How much is the variation in the potential energy of this electric field? Yes, EQS. To be precisely, we can put a minus symbol. Then, what is the difference in these two situations?
here we have electric, but there.
Yeah, there's not much difference between these two situations. And both is the transformation of potential energy into another kind of energy of the point. The only different thing is that is the potential energy caused by the gravity, and that is the potential energy given by the electric field. Therefore, there is a potential energy in the electric field, and it is much similar to that of these two situations. The interesting thing is the variation in potential energy has nothing to do with the exact path. When you move like this from A to B, the variation in the potential energy is exactly the same as that come direct from point A to B. That is a very important definition of potential energy, or the potential energy has a characteristic characterization like this. The variation in potential energy has nothing to do with the exact path. The only related to it is the start point and the ending point. Similar, same for gravity, for spring, and for electric field. Then we'd like to do a definition of potential energy because we want to do a calculation. The variation is not enough. We want to set some point. In the situation here, at the point A, the potential energy of this point that is due to the electric field, we can name it UA. And the point B, we name it UB with the symbol U and the point symbol B. That is the potential energy at point A and the potential energy at point B. The variation in the potential energy can be written by VA minus VB or zeta U. There's an exact explaining of the variation in potential energy. The work energy theory says that the change in kinetic energy during any displacement is equal to the total work done on the particles. If the only work done on the particle is done by conservation forces, like I say here, the conservation forces in the situation here is the force caused by the gravity. And in the situation 2 is the force given by the electric field. And you want to say if there is some difference between potential energy of gravity and the potential energy of the electric field is that the charge of Q can be positive or negative. the same electric field from the point from the up to the downside is E. If there is a positive charge point, when it moves from point A to point B, you will find the force on it is with the same direction of the movement of its body displacement. Therefore, the work done by the electric field is positive. The energy in this point is increased all the way from A to B, and the potential energy is decreased. The kinetic energy is increased. However, if there is a negative charge point, move same all the way same to that from A to B, you will find the force on the negative charge point is opposite to its displacement. Therefore, the work done on electric field on the negative charge is -2. The kinetic energy of the point may decrease and the potential energy is increased. So when we calculate or when we name the potential energy of a point, we have to know it is positive charge or negative charge, because the potential energy for the same moment, for the same displacement, the change in the potential energy is different when the charge is different. For example, as shown here, if a positive charge moves in the direction of E, the field does positive work on charge. Therefore, the potential energy of the electric field decreases. And when the positive energy moves opposite to the electric field, the field does negative work on charge, and the potential energy increases. However, for a negative charge, if it moves in the direction of the electric field, the field does negative work, and the potential energy increases, which is exactly opposite from that of the positive charge. Then, if a negative charge moves opposite the electric field, the field does positive work on charge. And in this situation, the potential energy decreases, also opposite to that of the positive charge. We can find it. Therefore, for the same electric field, the potential energy is different. For positive charge, the maximum of its potential energy is at the point from the beginning of the electric field. And for a negative charge, its maximum potential energy is when it is at the position at the end of the electric field. That is totally different. Then come from the easiest one, the potential energy of a point charge. We'll consider first, a displacement along the radial line from point A to point B. The force on Q0 is Q by volume square, and its radial component is force equals to 2 pi epsilon 0 below 1 and Q0 beyond R squared. If Q and Q0 have the same sign, the force is repulsive and the Fr is positive. If the two charges have opposite signs, the force is attractive and Fr is negative. What does it mean? For a point charge, the electric field around it is point from itself to a far away direction. And the point, the stem moves from a near position to a far position A to B. If it is a positive charge, this displacement results in an increase in kinetic energy and a decrease in the potential energy. However, if it is a negative one, the force between them is attraction. Therefore, when it moves from point A to point B, the potential energy is increased, where the kinetic energy is decreased, because the work done by the electric field is negative work if there is a negative charge, and it's a positive work if it is a positive charge. What we want to calculate is the magnitude of the work done by the point, because the force on the point is different at point A and point B. And we do Q and Q0 minus Q0. We also force, for example, at point A, R2. At point A, the force on point A that is given by large Q is Q0, 4 pi epsilon 0 R squared. However, at point B, that is large Q0, 4 pi epsilon 0 R2 squared. And when R1 is smaller than R2, the force on Q0 on point B is smaller than the force on Q0 at point A. So the work done by the electric field all the way from A to B is not, it cannot be calculated by F times the displacement. Because the force is a variation parameter all the way from A to B. It changes from R1 square for pi epsilon 0 Q0 to large Q0 for pi epsilon R2 square. That is a smaller one, a larger one. In this situation, an integral is needed. Integral is needed from force times displacement all the way from A to B can be calculated with work done by it. Since the force is a variation parameter, therefore integral. And finally, the result is here. Q0 or 5 epsilon. So A. There's R, B. The work done by it, which is related by the magnitude of charge, large Q. The magnitude of charge Q0, that is a constant, and influenced by the two distance from the distance of the point A being away from the large Q. And you will find constant. The only parameter that influence is the weight, is the distance away from it. Therefore, from A to B, only influenced by the start point and the ending point, as drawn in the PPT. If you go with another path, no matter what is, just from A to B, the variation in the work done by the electric field is all the same, because the work done by it is not influenced by the path. It's only influenced by the starting point and the ending point. If the variation has been defined, we'd like to have a new definition of the U, as we have named the potential energy. Need the exact definition to decide the variation in it. The U, how to define, we can name it as like here. If point A, the potential energy UA equals to Q0 or I equals 0 R1, the distance from A to large Q. And for UB, it equals to large Q equals 0 or I equals 0 R2. And the R2 is the distance of point B to the large Q. In this case, the variation in the potential energy, as shown here, can be easily written by UA minus UB. You will find some interesting thing. QQ will by epsilon R. How about the force between large Q and Q0? The force, large Q, Q0, or I equals 0, R square, right? Can you tell the difference of it? There's only whether there is a square of the R. The large Q, Q0, and the 4 pi equals 0. The part circled by the red is all the same. And the only different thing is whether there is R square or R. And without the square, it is a potential energy. With the R is the force on it. R square. With the square is a force. Without it is a potential energy. And then we are going to learn how to use the potential energy. A proton is released from rest. x equals to -2 centimeters. I think this question is very easy for you. Okay, there are two homework for you. The first one is a question number 1 here for number A, B, and C. And there's a homework number 2. There's a positive charge, large Q, at the point 0. When there is a Q0, which is positive charge, move from A to B and then from B to C. Find the work done by large Q on Q0. And the distance of OA is R1, distance OB is R2, distance OC is R3, distance AB is R4, distance BC is R5. Find the work done by large Q on Q0. And the question number 2. If the Q0 is replaced by the -2 Q0, how about the work again? Similar from A to B and then B to C. 2 homework, okay? Homework number 1, you can take a picture, and then homework number 2, you have the whole 1 week to finish it. The next week, I won't check your attendance. I will check your homework. If you have do your homework, you attended. However, without your homework, you are here, that is nothing. I don't, maybe you can't finish it by yourself. It is okay, just try your best. I wanted to see your try, no matter if it's right or not. That is both okay, right? Take a picture of both question 1 and the homework number 2, and hand it to me the next week on the class. And when you finish, the class is over today.
Because now can we get the PPT of God's law?
Of course, I might send to you after the class.
Okay, and you put that.